Welcome. Let's consider 100 unit cubes. Of course, they can be arranged into a big 10 by 10 square in one layer. But can we stack them up to get 4 perfect cubes? Better yet, what is the smallest number of connected flat one-layer blocks can we use? 10, 11, 12, all the way up to 100? We are interested in the smallest number in this case. It is a puzzle that challenges us to consider volume, structure, and mathematical arguments. Before we get started, pause the video and give it some thought in your mind or on paper. Let's begin by observing the diagram. Notice the quantities, shapes, and spatial layout. What would you need to know before determining if this transformation is actually possible? Use the provided sentence stems to help structure your observations and wonderings. The numbers invite us into the puzzle. We see that the sum of the volumes of cubes with side lengths 1, 2, 3, and 4 equals 100. However, a crucial distinction. Matching total volumes proves we have enough cubes, but it does not prove they can be connected to fit. To solve this, we must define our rules. A unit cube has dimensions of 1 by 1 by 1. A layer is a single cube-thick section. Pieces must be internally connected, and we can rearrange them by moving, turning, or flipping, provided we don't break the pieces apart. Why does 10 feel like the natural minimum? A flat piece can only occupy one layer of a completed cube. By calculating the layers needed for each cube, we arrive at a total of 10 layers. This creates a lower bound, but as we will see, it is not necessarily achievable. If we have exactly 10 pieces, every layer must remain whole. The claim is that these 10 squares must tile the 10 by 10 square. Consider this. What is convincing about this claim, and what still requires more proof? A systematic check helps us rule out 10. By attempting to place the 4 by 4 squares onto the grid, we find that every possible configuration hits a dead end, resulting in gaps or overlaps. We must now complete our argument. Why exactly do 10 pieces fail? The 11th piece fundamentally changes the geometry. By splitting a 4 by 4 layer into two connected pieces, A and B, we can fill gaps that a rigid square cannot. This split is essential to making the construction possible. With 11 connected pieces, we can finally fill the original square. This diagram shows how the volumes for each cube are represented, culminating in an 11-piece construction. The gold piece represents the 1 cube, blue the 2 cube, green the 3 cube, and purple, plus A and B, form the 4 cube. Let's trace these two unusual pieces. Here they are inside the 10 by 10 grid, and here they are reassembled into the 4 by 4 layer. Discuss with a partner. How do we know that neither of these pieces was broken during this process? To finalize our proof, we use a claim, evidence, and reasoning structure. Our claim is that the smallest number of pieces is 11. Our evidence comes from the volume requirements and the construction constraints, leading to the reasoning that 10 cannot be attained, but 11 can. When writing up your own proof for other people, use this structure. State why the volumes match, explain the layer constraints, describe the issue with 10 pieces, and use your diagram to show how the 11th piece solves the problem. We can extend our learning by changing conditions. What if the pieces had to be rectangles? Or what if we wanted to build cubes for 1 through 5? Mathematicians often ask these questions to test if their logic holds up in new scenarios. In summary, this puzzle is more than just counting cubes. It's about volume, structure, and rigorous mathematical reasoning. We started with an equation, but it took the discovery of that 11th piece to truly complete the argument. Thanks for watching.